find some time and then
Okay,
I'll
yeah.
upload them on Google. Oh,
Google Drive.
yeah.
Okay.
Okay. So let's try it before going to the solutions, maybe. So this is going to be A naught, Z naught powered by N plus A1, Z N minus 1. It's Z naught, keeps going up to some AN, some constant AN. If Z naught is a root, then this guy is it's gonna be a 0. Right?
You mean okay.
Yeah, the whole
You mean
polynomial.
whole equation.
The whole equation.
Whole polynomial.
Yeah, if Z naught is a root, then the whole equation is gonna become it's going to become
0.
a 0. Yeah. Let's see. Why?
Why is gonna be 0? I mean, polynomial if root is Z naught. We're talking that if Z naught is the root of this polynomial, and if if this root equals 0, oh no. You're saying that this polynomial equals 0 if its root is Z naught, right?
Yeah.
But it says Z naught bar.
So now we want to find out.
Okay.
So given that Z naught is a root, so the question is Z naught bar also going to become a root?
Okay.
Yeah.
Okay, got it.
So that's what they want us to show. So maybe we can just go to the solutions for us to be quick.
Yeah.
So taking complex conjugates on both sides, it was so simple, and it's done. You see what they did?
Like, give me a sec. Taking complex conjugates on both sides of the equation we get.
So they started like us because Z equals Z naught, then the whole polynomial will become 0.
Okay. And he just changing Z to Z bar?
Yeah, so this is what happened. A naught, Z naught to the N, A1, Z naught to the N minus 1, like that. AN minus 1, Z naught, AN equals 0, right?
Yes.
So he just took complex conjugates on both sides. So you take a complex conjugate there and take a complex conjugate there.
Okay. Oh, okay.
So because all these coefficients are real, they won't change. They will not change. So it's going to be A naught, Z to the N. If you take a conjugate, it's going to be a bar. You see, A1, Z naught, N minus 1 bar, all the way up to AN equals 0 bar. But 0 is a real number, so it's just 0. And so Z naught is a root.
It's the root of this polynomial.
Yeah, it's going to be a root of P of Z.
Yeah, okay. It was easy.
Yeah.
Let's move to another one.
Show that the sum of roots of a polynomial of degree n above equals negative A1
over A0
over A0.
Show that the sum of the roots of the polynomial of degree n above. Write the polynomial as A that
Okay.
Z minus Z1, Z minus Z2. But we don't have Z1, Z2.
We are just assuming that Z1, Z2, Zn, all this, they are roots of a polynomial.
Okay.
Yeah.
Where Zi belongs to n are the n roots of the polynomial. Okay. Okay, we need to So this is the sum of the roots of the polynomial of degree and above equals. We need
Okay.
to
Is this A1 or is it
A1 over, let's check in solution.
A1 over A0?
I mean, maybe, yeah.
So if we write it in that factored form,
Let's say 1 over A.
so
Gn minus Z1, Z2, that's Gn. Times Gn by root 4. Negative 1 powered by n. How he get it? How did he get it?
so he multiplied all the z's. Z times Z times Z, they became the Z to the n. And then he multiplied all the Z1, Z2, up to Zn, they became that.
Okay.
I can see what he did there, and I can see what he did there. But whatever he did here, so this is Zn minus 1. And then we're going to have Zn minus 2.
So he multiplied all these and he got Zn and minus all other part, which is Z1, Z2, all the way to the Zn.
Yeah, okay, let's just do it. So Z minus Z1, Z minus Z2, up to Z minus Zn. So if you multiply Z up to that, you get Z power n.
Yes.
And then if you multiply Z, you just keep multiplying them, but now you stop at this point, Z minus Zn minus 1. So they are going to become Zn minus 1 multiplied by Z minus Zn. That is if you multiply all those Z's.
No, we multiplied all these, and also after that we multiply all Z1, Z2 by all the way to Zn. And now we need to multiply Z to Z1, Z2, Z to Z1, Z to Z3, and what we've got in the middle of it. He taking summation of all Z1, Z2 to Zn, and multiplying to, but I don't understand why Zn minus 1. Where he get it? Where he get an A1?
Oh, where he got the A1, that's easy because, you know, whenever you're writing a polynomial, the second coefficient of Zn minus 1 is the A1. So this is the A1 in this case.
Oh, okay.
Yeah, so it's easy to understand it from there. The only tough part is how they are getting the negative A naught Z1 plus Z2 plus all the way up to Zn. Basically, it's a polynomial. It's a polynomial, and then the variable is the Z.
Yes.
The variable is the Z. So, and for any polynomial, and for any polynomial, okay, so it's always the n A1 Z n minus 1, A2 Z n minus 2. They keep going down.
Until just Zn.
Yeah. They just keep going down. Okay. Maybe we can let's keep this part.
Yes. Let's move on to another one. I will check it out with maybe other sources.
Show that the product of the roots of a polynomial in equation 1 equals -1 powered by n an over a naught. So to do that, we want to show
second one.
Yeah. So to do that, we can just go back and we can use this. They want to determine what the product of the roots is. You see, this is the product of the roots, right?
Yes.
And you can see that the product of the roots Z naught, A naught, negative A1, N, and then the product of the roots, that's Z1, Z2, all the way up to Zn, right? This is usually the last coefficient that happens to be An. So this product of the roots, Z1, Z2, all the way up to Zn, is going to be equal to An
over
-1 for n A naught. Yeah. So the product of the roots, they wanted us to show that it's going to be -1 power n An over A naught. But we have it the other way around. But it's going to be the same thing because the -1 doesn't matter if you put it on top or down below.
Yes, it doesn't match actually.
Let's see what they have. They have the same thing. So for this proof, we only need to know how they got this. At least we know how they got that. That's easy. The first one is also easy. But now the middle terms, that's all we need to know for us to do the first proof. And then for the second proof, we've already done it using the last term. Yeah. Okay. We go to number 2. Find all the roots of this equation. It's Zn minus 1 equals 0. This means that Zn equals 1. Which means that Z is going to be equal to
square root,
the nth root of that. Yeah. So if we were to draw this somewhere there, this is 1, and this is an angle theta, right?
Theta.
So this is going to be, so that's 1. Cos theta equals adjacent over 1. So simply, this is going to be cos theta, and this is going to be I
sinus
sine theta, because it's a complex number. So, so this is going to be cos theta plus I sine theta.
Square roots. Oh, I mean just root square. No?
Yeah. So this number, this complex number is going to be cos theta plus I sine theta, right? The complex number, which we could write as E I theta from Euler's formula.
Yes.
Right? So it's going to be the nth root of this. So this complex number Z, we could think of it as Z equals EI theta. And then we could say that
square root
the roots, the nth root, this is Zn. Zn equals EI theta. So it's going to be Zn equals EI theta divided by n, right?
Yes.
No,
but we need to take n.
There is no n. Yeah, there is no n from Z. Okay. And remember, this can go again, which we could do also.
Yes.
E I theta plus
pi
2 plus 2 pi over n.
Over n.
Right? Which we can call 2 pi k over n. Yeah.
Yes.
So the roots are going to be E I theta plus 2 pi k over n, and we have to insist that k is less or equal to n. Let's see what they did. Yep, exactly what. Yeah. So instead of writing that k is less than or equal to n, actually k is less than, strictly less than n. They said that k is going to be equal to 0, 1, 2, n minus 1. but at least they didn't show us how the EI theta is coming from. They assumed you already know the Euler's formula. Yeah.
Yes, I see.
Okay.
Cool.
So far, so good, not so hard. Okay, find all the roots. So we already have that. So use these roots and problem 1b above to show that for n equals 2, 3, 4 all the way, this guy is going to become -1, and this other guy is going to become 0. Okay. We already know from they're saying use these roots and problem B to show that for n equals 2, 3, 4 all the way, this guy will always be -1. Problem 1b. So let's see how they did this.
Again, 0.
Cause that. How? From the result we get in problem 1b, we know that the summation of roots equals all these roots. All of them, and it's going to be -1 over -a1 over a.
No. Okay, maybe it's better to keep this one. Come back to it later.
Okay. So find the roots of the two equations. This is Z5 plus 32. So Z powered by 5 equals 32.
-32.
Equals -32.
Z square. Oh.
So this is Z powered by 5 equals -32 multiplied by 1, right? And we already saw that 1, Z powered by 5 equals -32 e to e I theta plus 2 pi k.
2 pi k.
So if you take the fifth root, it's going to be the fifth root of -32 e I theta plus 2
pi k.
Pi k over 5. But now k is going to run all the way from 0, 1, 2, 3, 4, right?
Okay, yes.
So Z1
is
going to be equal to the fifth root of 32. And then this is going to be E.
You're forgetting minus.
Yeah.
Okay, no worries.
Yeah.
I think it's not big. we can just say that it's times to I square.
Yeah, it's a big deal. So we should write negative like that. So this is going to be I theta, right?
Yes.
So Z2 is going to be 5th root. You know, K is 0. So EI theta over 5.
Oh, okay.
K is 0. Okay. So the second one is negative 32. E I theta
plus 2 pi.
Plus 2 pi over 5.
Over 5.
And then the third one, the third root is 5th root of negative 32. E I theta plus 4 pi over 5. And they keep going. So we are going to also have Z4 and Z5. The only thing that's going to change is that in Z4, it's going to be 6 pi. In Z5, it's going to be 8 pi. And then we stop there.
And this is the roots of our equation. Okay.
Yeah. And you can see.
But it's only 4. Yeah, it's the same how you said.
Yeah.
But he changed the sign. It's positive. I think it's just mistake because it's supposed to be Z5 minus 32, not equal. I think it's just a small mistake. Oh, look at here. He's providing 2i. He's opening it.
Okay, EI 2. Okay, EI. Pi plus 2k pi over 5. Okay, I'm trying to think how he managed to escape the negative. Could it be a mistake on his part?
I think it's just no, it should be minus 32. Minus 32.
Okay. We will look into it next time. Maybe there was a mistake, or maybe he has the right to do it. We don't know. Yeah. Oh, and the 5th root of 32 is 2. Okay.
Well, what did you say?
Yeah, I'm just saying that the 5th root.
Okay.
The 5th root of 32.
Oh yeah, it's
just
2 by 2 4, 4 by 2 8, 8 by 2 16. It's 16 by 2 it's 20, 32.
Okay, so in the next one we have Z3 is going to be equal to 1 minus I multiplied by EI pi plus 2 pi
k.
Okay. What is the cosine of pi?
Let me check very quick.
The cosine of
Cosine of pi it's -1.
And the sine of pi?
sine of pi is 0.
I see why he kicked out the negative. I see how he got the 2. Let me just take you back to this. You know, this is z power 5 equals negative 32, right?
Yes.
Times 1.
1.
And then z5 equals
Negative 32.
Negative 32
times
E.
I. But I don't understand why he put I. It should be I theta, right? Oh no, it's a I pi.
It's I pi because you know E I pi is the same as, according to Euler's formula, it's going to be cosine of pi plus I sine of pi.
I sine pi.
And the cosine of pi is negative 1. Cosine of pi is negative 1. And so that is why, to make it 1, this has to be negative. EI pi is negative 1, right? Because this is 0 and this is negative 1. So EI pi is negative 1, right?
Yes.
Negative times negative, positive.
Plus positive.
Negative times negative is positive. So this is Z5 equals 32 EI pi.
But why is they using EI pi? Why it's not a theta?
It's not theta because you see, we have to ensure that whatever we have, we are substituting 1, right?
Yes.
You see, EI theta is not defined. You cannot say that EI theta equals 1, but you can easily say that negative EI pi equals 1. So we are using negative EI pi as a substitute for 1. Yeah.
Okay. Yeah, got it.
Yeah. And
now
so
I see.
Yeah. So EI pi like that, and we are allowed to do a plus 2 pi k as well, because we can keep making complete revolutions around. So if we come back to this is going to be z cubic equals negative 1 plus I multiplied by 1.
Yes, and we can write negative 1 plus I times E.
So this is going to be z cubic
again EI pi
equals negative 1 plus 1, negative 1 plus I times negative E
I pi plus 2 pi k.
And it's a negative EI pi.
Yes.
Which is going to become z cubic plus z cubic equals 1 minus I
times E I pi plus 2 pi k.
plus 2 pi k. And so this is going to be z equals cube root
pi. Oh yeah.
1 minus I E I pi over 3 when k is 0, right? And then the other one is going to be EI pi plus 2 pi over 3.
Right? Over 3, yes.
And then the other one is going to be EI pi plus 4 pi.
Yes, plus 3. 4 pi over 3. That's it. We don't need to open, use Euler's formula to find cosine and sin, right? We can leave it right you're saying. It will not be a mistake.
Yeah, we can leave it there, but okay. I think it depends much on the Why did he do 3 pi over 4?
When it's case 0, we're finding Z1, which is 2. How he get 2? Okay, square root 1 over, okay, square root, it's 1 over 6, okay, times, it should be just I pi over 3, right? Two powers 1 over 6.
Oh. The 3 pi over 4 is coming from the -1.
Plus 2k pi.
Oh. I see. So you have to graph it first. You see the vector -1 plus I, you have to graph it. -1 and then I, and then you use this angle to do your E, you use that angle to create your exponential formula.
Mm-hmm.
Yeah.
Okay. The angle of theta changed.
Yeah. Okay.
Mm-hmm.
Hello? Hello? Yeah, I guess we got disconnected for Can you hear me?
Yes, I can.
Okay. So they want us to find and plot this region.
Mm-hmm.
So Z minus 3 over Z plus 3 less than 2 in the Z plane. So how did they plot it? Let's see.
Z minus 3 less 2 times Z plus 3. 0 on X plus IY. X plus IY negative 3 minus 3. But why it's plus? Why?
Where? So let's just look at it. So they started with the Z minus 3
minus 3 over Z plus 3
less than 2. So you could just do Z minus 3 less than 2, Z plus 3.
And Z plus 3.
And then if you introduce the X plus IY minus 3 less than 2, X plus IY plus 3. So because the 3 is real, you could combine it with the X. So the real part becomes X minus 3 plus IY.
Plus IY.
And then this becomes X plus 3 plus IY.
Plus IY.
You know how we find the length of a vector? It's X minus 3 squared plus. So it's going to be a minus because I squared is negative 1.
Yes, that's what I'm
minus Y squared square root. And then this is going to be less than square root X plus 3 squared.
The same here. Minus
Y squared.
Yes, Y squared.
And so we could square both sides. We can square both sides and get X minus 3 squared minus Y squared is less than 4.
No, just X minus 3.
Huh?
Why? Well, oh, okay.
Yeah, I squared both sides. So that's going to be 4X plus 3 squared minus Y squared, right?
Yes.
And then the Y squared
they're canceling out.
They seem like they cancel out, which is not good. It's not good for them to, and also they cannot cancel out because this is a 4Y squared. They can't cancel out.
Oh, yes. Right. 4.
And so this is going to be X minus 3 squared minus 4X plus 3 squared less than
minus 3Y squared.
Minus 3Y squared. And then now we can open this. If we open
or we can just tell that it's 3x plus 3 squared. Oh no, it's x plus and x minus. No, we can't.
So it's going to be
it
x
will
squared,
be x squared
minus 6x plus 9 minus
4x squared
plus 6x plus 9, which we could simplify.
Yes.
This becomes
minus
3x squared minus
5 times 6x
minus 30x.
30x. Yes, and 4 to 9, 36, 27 minus 27
is less
than minus 3y squared.
Minus 3y squared. So you divide everything by negative 3, you get x squared.
X squared minus plus 10x plus 9.
Plus 9 is greater than y squared.
Less than. Yes.
It's greater than y squared. So we take this part and we complete the square. So if we complete the square, we could do x squared.
Oh, he's adding 25.
Yeah, we could do x squared plus 10x plus 25 minus 25 plus 9 greater than y squared. So you see, we added 25 and we subtracted 25. And so this is a perfect square that can be written as
it will be x plus 5 squared.
Plus 5 squared.
Plus 5.
And then minus 25 plus 9.
It will be 16, negative 16.
Negative 16 greater than y squared. So if you interchange the y squared and the 16, you get y squared plus x plus 5 squared greater than 16.
Yes.
Greater than 16. So this is going to be a circle. So you're going to have that. So it's going to be a circle centered at 0
and 5.
5.
Negative 5. Negative 5.
So it's centered there, negative 5. And the radius is 4.
Yes, radius is 4.
And we want the greater than region. Yeah.
It looks like geometry, which we did in school.
It's more of geometry. And there you go. There you have.
Yeah. It's cool.
So consider that map. Oh no, whenever I'm teaching you, time flies so quickly.
Yes.
So I'm looking at number 5 and then I'm looking at the time. And
yes, that's it. Only 6 minutes left.
So consider the map, this map. From the Z plane to the W plane, show that the lines that map to hyperbolas in Z plane. Plot these hyperbolas. So U, it's a function of x, y, and then it's a plus minus 2. And then V plus minus 2. Okay, so this is Z squared is actually x plus IY squared, which is actually x squared plus 2i
x, xy
xy
minus y squared.
Minus y squared. So this is x squared minus y squared plus
2ixy.
I 2xy. And so this is U.
This is V. And it says it shows that the lines U plus minus 2 and V plus minus 2.
So
we can find the coordinates, right, of xy.
Yeah, let's see. So x squared minus y squared equals 2, right?
Plus minus 2, no?
Equals 2, and then we can have x squared minus y squared equals negative 2.
Okay.
These two are equations of a hyperbola.
Yes, I agree.
And then 2xy equals 2, meaning that xy could be equal to
1
and xy could be equal to negative 1.
Okay, now we can express, for example, x equals 1 over y.
Yeah, so y equals 1 over x.
Oh, 1 over x, yes. And x squared negative 1 over x squared.
And y equals -1 over x. So basically, this is the equation of, this is the reciprocal function, right?
Mm-hmm.
And this is clearly the equation of a hyperbola.
Mm-hmm.
And so we just need to graph it. It's going to be centered at the origin. So let's just look at the graph and then we can see how they did it. Yep, they did it like us. Oh yeah, and they drew it. They drew the hyperbolas x squared minus y squared centered at the origin. And they also drew this rational function 1 over x. The rational function 1 over x is this one. And then the rational function -1 over x is this one. And then the x squared minus y squared is one of these. And the other one is that one. So there you go with the hyperbolas. So I guess the only thing we need to do is figure out this. And this is actually based on algebraic identities. Yeah. So I'm going to look up expansion of n-dimensional algebraic identities. You know, for example, if you have A minus B, A plus B, this is like a simple algebraic identity. So there must be another identity that's going to help us through this one. So we will look it up soon. Let's see. So I think if this was an exam, you know, I'm still preparing for your exam. So I'm like, if this was an exam, question 1 would be 60%. And then all the others are good. Yeah. This would be 100, 100, 100, and maybe this would be a 70.
He said that he will provide a list of themes which we need to review for the exam. And he said that he's not gonna put SVD decomposition to the final exam. I don't know why.
Because it's the easiest thing that we have studied so far.
Maybe.
Yeah.
Yes, actually, this is the reason. So yeah, that's, I think maybe we can do it, spend 1 hour on. Also, Steven, I had a question. My classes with Preply are done. I mean, like I need to renew them. I mean, to buy new hours, or we can just work as a PayPal or
we can just do PayPal.
PayPal.
Yeah, but we really need to schedule on Google Meet.
Google Meet.
Yeah, okay. You need to schedule your classes on Google Calendar, not
Google Calendar.
You know how to schedule events on Google Calendar?
No, actually, no.
Yeah.
I will check it out.
Yeah. So maybe I could show you. For example, if I go here, my calendar is already here. I can see it. So, for example, I met a student who pays me via PayPal. You see this 6 to 7? Yeah, this one is PayPal. This one is Preply. This one is Preply. So the beauty of Google Calendar is that it prevents crashing. So if you schedule, you will not be crashing with any other.
Okay, yeah, I'll do it.
Yeah. All right.
Okay. Okay, Steven, so I scheduled another class at 11. See you in a few hours, okay?
All right, see you soon.
See you, bye.
Bye. Oh,